Hi friends, now we will discuss on the topic direct liquefaction of coal. In the previous class we have discussed on gasification of coal and we have seen that coal is gasified to produce syngas and that syngas can be used for different downstream application. One application was FT synthesis, that is the Fischer-Tropsch synthesis through which we can get different types of liquid fuels. So, that liquid fuel production from the coal was an indirect route and this is important, the production of liquid from the coal, because we can use liquid fuel more easily in different engines, and if we want to produce it through this indirect route, then obviously it is involving number of steps, conversion steps. So, more the steps, lesser the efficiency, overall efficiency of the process. So, people thought if the coal can be converted directly to liquid, and in the introductory class we have seen that coal contains different aromatic rings, a chain of aromatic rings we have seen like this, very bigger, it is very complex structure, that is why it is solid and less reactive. It is not that high reactive, we have to heat it at higher temperature, then only there will be some combustion. At lower temperature there will be no combustion, unlike say plant materials. So, that is why it is solid. Now, and here also we know that carbon concentration is also very high with respect to hydrogen. Now, if we can break this, some of the rings here and say some double rings are there, see if we can break some double ring and we can add some hydrogen here, these rings, then it will be converted to some organic compound having lower molecular weight, and that will be in liquid form, that can be in liquid form. So, we will be able to get liquid fuel from coal by this process, but what is needed here for this conversion? One is hydrogen, we have to provide sufficient amount of hydrogen, and as you know coal is not that reactive. So, hydrogen has to be provided at higher pressure. So, high pressure hydrogen is required, and coal particles has to be particle size will be very small. The very small particles will be made slurry in some solvent, and then solvent coal slurry, obviously more solvent is required, and then hydrogen at high pressure, that will be giving us this conversion, that may give us this conversion. And if we can use some catalyst, the rate of the reaction can also be improved. So, that way directly coal can be converted to liquid, and as you have discussed that this technology was developed many years ago in Germany in lab scale or small scale production, but for commercial scale production very recently the plant has come in China. So, we will discuss here, and our content is direct liquefaction process and then properties of coal derived liquids, then types of direct coal liquefaction, that is single stage direct liquefaction process or two stage direct liquefaction process, and then we will see the benefits of direct liquefaction process and direct liquefaction challenges. Now, we see in direct liquefaction process different coals are converted to coal liquid. It can may be lignite or brown coal, it may be subbituminous, it may be bituminous coal. Very interesting here, lower the quality of coal, more easy to convert it into liquid fuel, and you see here anthracite is not shown. So, when we are getting the coal liquid, we compare the heating value with respect to these different types of coals, this is much higher than this. So, energy intensity is increased in the liquid fuel, that is one advantage, and we see here we need hydrogenation step, we need hydrogen and catalyst, we need high temperature and pressure. So, these are the requirement for the direct liquefaction of coal. Here any type of coal can be used, there is no limitation of its quality, but preferably lower quality coals can be used, and then we will get gas oil, gasoline and kerosene. So, this is the overall process for direct liquefaction of coal. So, it is accomplished under high temperature, that is around 400 or more than 400 degree centigrade and 102 to 204 atmospheric pressure, very high pressure it takes. So, what will be happening? Just we have discussed, the coal is fragmented, the complex structure is broken down and it is fragmented, and then hydrogen addition takes place. So, we will be getting some coal liquid, that coal liquid may be requiring for further upgradation, that is obviously for hydrogenation, that we are going to discuss. So, now we are having coal, this coal we are getting coal fragments, and this is what is the process? The dissolution, hydrocracking and hydrotreating, heat, pressure and catalyst. So, coal slurry formation, then application of heat and pressure, may be catalyst or may not be catalyst. So, that will be getting coal fragments. Then coal fragments will be having some oil part and some also solid part it will be having. So, that solid part is called pre-asphaltenes or asphaltenes, that is having high molecular weight. Then what we will do with this? Another step we can go for hydrocracking, catalytic hydrocracking. So, we can get more oils from this asphaltenes part also, and then further hydrotreating will give us transportation fuel. So, hydrogen addition may not be in a single step, it may be stepwise. So, we can increase the hydrogen concentration in the liquid and it will be more usable from in transportation fuels. Now, properties of coal derived liquids, we see this table shows us the properties, that is density, viscosity, potential aromatic percentage, sulfur, nitrogen, Cetane number, flash point, solidification point, coal filter plugging point and oxidation sludge. So, it is also given. So, naphtha which is generated from the coal liquid and diesel, these two properties are shown here, and this table we can see that the comparison of some properties with say, and we can get the Cetane number here. So, Cetane number we can have diesel around 50, here we are getting say 46.7. So, relatively lower than that, but as the coal liquid is coming from the coal which is having very complex aromatic structure. So, aromatic compound in coal liquid will be more. So, octane number will be higher in case of that, but Cetane number is not that higher with respect to the petrodiesel. So, direct coal liquid naphtha can be used to make very high octane gasoline component. So, that is one advantage of this or the positive point of this or in terms of the quality of the coal liquid, coal derived gasoline. And DCl distillate is a poor diesel because this value, that Cetane number is lower than that of the petrodiesel. And raw DCl liquids still contains sulfur, nitrogen, oxygen, possibly metals also, and so we need to upgrade this for the removal of these components from the coal derived liquid for its effective application. Now, we will see what are the different steps through which the liquid fuel can be produced from the coal. So, we have one single stage direct coal liquefaction or double stage direct coal liquefaction. So, the single stage, that means gives distillates via one primary reactor, and double stage gives distillates products via two reactor stages in series. So, coal dissolution in first stage operated either without a catalyst or with only a low activity disposable catalyst. So, in case of single stage reactors, there are some technologies like SRC2 and then Exxon donor solvent, EDS and H coal. And for double stage, we are having integrated two stage liquefaction ITSL and catalytic multi stage liquefaction CMSL. Now, we will see SRC2, that is solvent refined coal liquefaction, solvent refined coal liquefaction. So, we will be using solvent only, no catalyst will be used in this case. So, we are using coal here crushed and grinded very small particles, then we have to make a slurry. So, I need some solvent. So, where from we will get the solvent? It will be coming from the process which is generated in the process. This is heavy distillate, it is recycled back and it is creating this slurry. So, when this slurry is coming, I need hydrogen. So, hydrogen we may get from the gasification process using again some amount of coal here, and this hydrogen is coming here, or we can get the hydrogen here also which is produced in this process. So, then hydrogen addition is made, slurry is formed. So, we have to pressurize it. So, after slurry preheater, it is coming to dissolver where high pressure of hydrogen is created. So, 12 megapascal at 440 degree centigrade. This 15 to 45 minutes time period is required here without any catalyst. So, this will give us the conversion. So, what we will get? We will be having the mixture now, we will be having vapor liquid separation where the vapor, the hydrogen which we have added, they can be recovered, and we are also after gas separation we will get the fuel gas, and solid part will come here, then it is coming slurry light liquid separation at 1 megapascal and 290 degree centigrade. So, we are getting light distillate naphtha and then again filter, then residue. So, this residue is your solid part. So, this is again used in the gasifier for the hydrogen production, and this liquid part from this filter it will be having the heavy liquid. So, that heavy liquid will be distilled or heating and vacuum distillation, then it will give us heavy distillate fuel oil, and wash solvent will be coming as a vapor and that can be recycled, and this it will give us SRC coal, that is solvent refined coal, that the rest part which is remaining. Now, we are coming to Exxon donor solvent process. So, that is also one step process. So, here coal slurry making, where the solvent is coming from the process which is generated during this process, and then recycled solvent slurry making, hydrogen is coming from this process and it is preheating, then it is going to tubular reactor. So, a condition is 425 to 450 degree centigrade and 175 atmospheric pressure, no catalyst is used. In this case pressure is higher than the previous one, temperature is also slightly higher or in the same range, but the pressure is higher. So, then it is coming for separation. So, gas separation hydrogen will go here and then we will go for liquid separation. So, we will get naphtha and we will get distillate fuel. Then from the solid we can get flexi coker and coke formation here, and that liquid will also go here. So, then and from this part we will get some liquid that can be going through hydrotreating to improve its quality, and that can be used as a recycled solvent. So, this is the flow sheet of EDS process, that is Exxon donor solvent process. The yield can be up to 47% for lignites, 50% for subbituminous and 60% for bituminous type of coal. Now, H coal process is another process which is also single step process, and this reactor operates at temperature 425 to 455 degree centigrade, and here conventional supported hydrotreating catalyst either nickel molybdenum and cobalt molybdenum in alumina is used. So, unlike to other process, in this process catalyst is used, and H2 is added and mixed in a preheated and fed to an ebullited bed hydrocracker. The hydrocracker reactor bed is also not fixed, unlike the other process. So, here the yields are dependent on coal and greater than 95% overall conversion can be obtained, because we are using the ebullited bed reactor, and yields liquid yields up to 50% on dry basis. So, as we are using the ebullited bed reactor, it has some advantage, that is well mixed and temperature monitoring. So, that is giving some better efficiency than the previous one. And then HCOL process. HCOL process, this is derived, it is developed by HRI, Hydrocarbon Research Incorporation, and currently Hydrocarbon Technologies HTI USA, and in this case ebullited bed reactor is used. So, pulverized coal, recycled liquid, hydrogen and catalyst are brought together in the reactor to convert coal into hydrocarbon liquids and gaseous products. Just we have discussed these things, and similar way this also takes place, and particle size is minus 60 mesh, and temperature 345 to 370, and this is 445 to 455 degree centigrade, and up to 200 bar pressure, and catalyst is cobalt molybdenum and alumina. So, this is one technology which is used for the direct coal liquefaction. So, now two stage liquefaction if we see, the one is our ITSL two stage liquefaction. So, here we see we are using coal here. So, that coal we have to make slurry. So, some solvent is needed. So, those solvent will also come from the process. So, here is after Rose Esser solvent recovery, and another is your solvent recovery in this hydrogenated solvent recovery. So, these two solvent sources it is coming and making the slurry. Then this slurry, the first step will be catalytic first step. So, here hydrogen is added, then it will go to catalytic second stage, again hydrogen will be added, then it is going for hydrogenated solvent recovery. So, hydrogenated distillate we are getting, and then the solid the heavier part, that is resid plus ash, then we will go for solvent recovery, and that is residuum oil supercritical extraction, that is ROSE, residuum oil supercritical extraction. This method if we use, we will get here ash contents, and heavier solvent will go to this. So, this is the flow sheet of this two stage liquefaction process. Here we can get 170 atmospheric pressure, and here 343 to 412 degree centigrade for the first step, and the second step 432 to 440 degree centigrade. Now, CTSL process, that is also two stage process. So, it is ebullited bed reactor in both the stages. In the first stage 400 to 400 degree centigrade, second stage 435 to 440 degree centigrade. The lower first stage temperature provides better overall management of hydrogen, and also it is 200 bar. So, what is the difference between these and previous one? The nickel molybdenum catalyst NiMO on alumina, and CTSL process produces liquid product yield with low heteroatom concentration and high H by C ratio, hydrogen by carbon ratio. The product is closer to petroleum. Another is HTI coal process. So, HTI coal process again two stage process. So, the difference is that this uses their proprietary catalyst, a dispersed nanoscale iron based catalyst. So, in the CTSL process we had nickel molybdenum on alumina catalyst. Now, HTI coal process we are having GATE TM catalyst, that is nanoscale iron based catalyst, that is the most important difference. And coal slurry prepared by mixing pulverized coal and catalyst with process derived recycled solvent is fed in the reactor 435 to 460 degree centigrade. In the first stage, obviously the breaking of the coal structure, and the second stage is for liquefaction, and then this process is used at China Shenhua project in 2008, that is having the capacity of 3.5 million metric ton of coal producing with 1 MMT of oil. This is the Shenhua DCL project flow sheet. So, you see coal is here, slurry preparation takes place, catalyst is added, solvent is coming from the process derived solvent. So, it is coming, and then this is going for liquefaction reactions, then separation, then hydrogen recovery, hydrogen will come, and hydrogen recovery will get here. So, then the liquid part go for hydrotreating, it will give us liquid, and then by distillation different fractions of liquid we will get, and from this part bottom of this, the residual part we can go for gasification and hydrogen we can make. So, that hydrogen can be used here. So, this process is used commercially, and this is the first plant in the world on DCL, direct coal to liquid, that is first DCL commercial plant in China. Production capacity is 24,000 barrel per day, and this 4 year of construction 2004 to 2008. These are the some photographs of different fuels derived from the coal directly in this Shenhua DCL plant. Then catalytic multi-stage liquefaction. So, in this case more than 2 step is allowable or used. In 1993, 2-stage liquefaction system evolved into catalytic multi-stage liquefaction system. In 1993, Department of Energy awarded HRI a contract to conduct demonstrations of direct coal liquefaction in 3 ton per day capacity, that is for demonstration plant. Okay, so, different types of catalyst has been used. You see the same company HRI, they are developing the technology. So, here supported catalyst CO, molybdenum, CO nickel, and dispersed catalyst FeMO and HTI proprietary GelCat iron based catalyst. So, now we will see the what is the scope of DCL process in India. So, we do not have any DCL plant in India, but this is Oil India Limited, Gluagen, they are putting their effort to develop the technology, and they are targeting to use the low ash content Assam coal for this purpose. And one study was going on, I am not aware about the latest status of it, and IIP Dehradun was contributing on the upgradations of the coal liquid. And what are the benefits of liquefaction? The direct liquefaction technology has higher efficiency, you see 70 to 75%, just we have discussed that when we are involving more steps, obviously the efficiency will be less. So, in this case we can get higher efficiency with respect to other technologies, say IGCC like this indirect way 60 to 65% maximum we can achieve. And then direct liquefaction provides high octane, low sulfur gasoline and distillate that will require upgrading to make acceptable diesel blending stock. So, these are the advantage, and development of direct liquefaction technology could lead to hybrid processes producing high quality gasoline and diesel, and direct liquefaction may have better carbon footprints than indirect liquefaction process. But what are the challenges? Uncertainty in oil prices. As you know, this method is not very cheap method, it will be costlier and will be feasible only when the crude price will be very high. It is feasible when the crude price is more than $70 to $80 per barrel, and high capital cost, as you see that high pressure systems are required. So, high capital cost is also needed, and then investment risk is also there that the market, what will be the value of crude oil, it fluctuates. So, what will be the stability of the market of this, that is also uncertain, and so it is, there is a risk for the investment on this. And technical challenges, this is this process was discovered many years ago, but commercialization take only in 2008, because there are many technical challenges. Although there is one plant, commercial plant in China, but still more research is required on this field, and to make it to develop confidence on the technology, LCA can be done. Okay. So, hybrid technology needs development including integrated demonstration and environmental challenges. It has some challenges also, carbon dioxide and criteria pollutants as well as water use. So, these are also related, these are not well addressed on this plant. So, thank you very much for your patience.